Look up at the night sky. For billions of years, the moon has hung silently above us, a barren desert of gray dust. But today, that dust is the foundation of a silent gold rush that could change the course of human history. Imagine a scenario where just 2 cargo bays of a heavy-lift rocket filled with lunar soil could power the entire United States for a full year. No carbon emissions, no radioactive waste, just pure, limitless energy. This is the promise of helium-3. On Earth, this isotope is so rare we have only managed to collect a few hundred kilograms. But on the moon, it is a different story. Billions of years of solar winds have deposited over 1 million tons of it into the lunar surface. Now, global superpowers and ambitious billionaires are racing toward the lunar horizon. This is the greatest resource scramble in history, a battle that will redefine global power and the energy markets of the next century. Why has the far side of the moon become the strategic front line? And is the cost of lunar mining a visionary investment or a trillion-dollar gamble? Today, we are diving into the battle for the moon's ultimate treasure, helium-3. To understand why the world is obsessed with lunar dust, we need to dive into the engine of the cosmos itself, nuclear fusion. This is the process that powers every star in the sky, including our own sun. For nearly a century, we have dreamed of capturing that power, of building a miniature star right here on Earth to provide us with infinite, cheap electricity. But not all stars are created equal. Currently, our most advanced fusion experiments, like the massive ITER project in France, rely on a mixture of deuterium and tritium. When these 2 isotopes smash together, they release a staggering amount of energy. However, 80% of that energy is carried away by high-speed neutrons. These neutrons are a nightmare for engineers. Because they have no electrical charge, they cannot be contained by magnetic fields. Instead, they fly out of the plasma and slam into the walls of the reactor. Over time, this microscopic bombardment makes the reactor structure itself radioactive and brittle. It is like trying to hold a sun inside a cage made of glass that is slowly being shattered from the inside out. It's dangerous, it's messy, and it's incredibly expensive to maintain. This tiny isotope changes the physics of the entire game. When you fuse helium-3 with deuterium, the reaction is what scientists call aneutronic. Instead of those destructive high-speed neutrons, the reaction produces a positively charged proton. This is the ultimate breakthrough. Because protons carry an electrical charge, they can be manipulated and steered using powerful magnetic fields. This allows us to use something called direct energy conversion. Instead of using heat to boil water and spin a steam turbine, a method that is centuries old, we could theoretically capture the electricity directly from the magnetic field of the reactor. It would be the cleanest, most efficient power source in human history. No long-lived radioactive waste, no meltdown risk, no subatomic shrapnel. So why haven't we done it yet? Because the barrier to entry is astronomical. Fusing helium-3 requires temperatures of nearly 600 million degrees Celsius, roughly 6 times hotter than the core of the sun. We are pushing the very limits of materials science and magnetic confinement. It is a challenge so difficult that some call it impossible. But with 1 million tons of the fuel sitting just 3 days away on the lunar surface, the prize is simply too big to ignore. If helium-3 is the perfect fuel, the ultimate solution, then why aren't we mining it right now? The answer comes down to a brutal reality, the sheer, uncompromising scale of the economics involved. On the current market, helium-3 is one of the most expensive substances on Earth. It is valued at roughly $20 million per kilogram. At that price, a single ton would be worth a staggering $20 billion. On paper, it looks like the greatest business opportunity in the history of our species. A literal moon-sized gold mine waiting to be claimed. But the market price is only half the story. The cost of admission is astronomical. You don't just land on the moon and pick up glowing rocks of helium-3. The isotope is spread incredibly thin, trapped within the top layer of lunar regolith at concentrations of just a few parts per billion. To extract a single ton of helium-3, you would have to excavate, sift, and process over 100 million tons of lunar soil. That is an amount of Earth moving comparable to digging the Panama Canal. And you cannot just dig it up. You have to heat that massive volume of dirt to over 600 degrees Celsius just to force the gas out. This requires an industrial infrastructure on a scale we have never attempted off-world. We are talking about fleets of thousands of autonomous mining rovers, sprawling solar arrays to generate the necessary heat, and cryogenic refineries to liquefy the gas for transport. All of this must operate flawlessly in the most hostile environment imaginable, a world with no air and a constant rain of micrometeorites. For decades, the cost of simply getting that heavy equipment off the Earth made the whole idea a non-starter. But the math is rapidly changing. We are currently witnessing a revolution in launch technology. With the development of next-generation, fully reusable heavy lift systems, the traditional barriers to space are crumbling. Companies are designing massive rockets capable of carrying over 100 tons of cargo at a fraction of Apollo-era prices. By drastically dropping the transport costs, the trillion-dollar gamble suddenly transforms into a viable, long-term business plan. However, economists warn of a potential lunar bubble. This is the ultimate economic paradox of space mining. If a company successfully brings back hundreds of tons of helium-3, the extreme scarcity that drives its $20 million price tag instantly vanishes. The supply suddenly floods the market, which could collapse before the first commercial reactor even turns on. Are we looking at the dawn of a new industrial revolution or a multi-billion-dollar graveyard of abandoned lunar tech? If we're going to build this unprecedented industrial complex, we have to decide exactly where to put it. And the answer introduces a whole new layer of extreme difficulty. We cannot just set up shop on the nearest, flattest crater we see from Earth. We have to go to the far side of the moon, the hemisphere that permanently faces away from Earth. To understand why, we look at how helium-3 gets there. It is not native to the lunar bedrock. It is born in the violent fires of the sun and hurled outward via the solar wind. For billions of years, the moon has been bombarded by this continuous stream of high-energy particles, acting like a giant sponge soaking up the rare isotope. Because the moon is tidally locked, the near side, the familiar face we see in the night sky, is partially shielded by Earth's massive magnetic field. Our magnetosphere acts as an invisible umbrella. As the solar wind sweeps past, Earth deflects a significant portion of those particles away from the moon's near side. The far side, by contrast, enjoys no such protection. It constantly faces the deep expanse of space, taking the full, unfiltered brunt of the solar radiation day after day. Because of this, the concentration of helium-3 on the far side is substantially higher. If you are gambling trillions of dollars, you have to go where the ore is richest. But operating on the far side comes with a terrifying logistical nightmare, a total communication blackout. Radio waves travel in straight lines. If your multi-billion-dollar mining fleet is operating on the far side, there's roughly 3,500 kilometers of solid rock between your machines and mission control. You are completely cut off. Imagine running a massive industrial operation in total silence. You cannot stream live telemetry, you cannot remotely pilot delicate machinery, and if something goes catastrophically wrong, you cannot call for help. To mine the far side, we first must build a dedicated constellation of relay satellites in lunar orbit just to bounce signals over the horizon and back to Earth. Before we can dig a single trench, we have to wire the moon for Wi-Fi. And geopolitically speaking, whoever builds and controls that network ultimately controls the far side. As the first relay satellites wink into existence over the far side, a new and dangerous question emerges. Not how we mine the moon, but who is allowed to own it. This isn't just a scientific hurdle, it is a legal and geopolitical minefield. For decades, space was governed by the 1967 Outer Space Treaty. It is a Cold War-era document that explicitly states that no nation can claim sovereignty over any celestial body. According to the letter of the law, the moon belongs to everyone and no one. It was designed to prevent the moon from becoming a nuclear launch pad, but it never anticipated a multi-trillion-dollar energy rush. It's a loophole you could drive a lunar rover through. Today, that treaty is being tested to its breaking point. While a nation cannot technically own a crater, modern interpretations like the Artemis Accords suggest that if you extract a resource, you own that resource. It's the difference between owning the ocean and owning the fish you catch in your net. But on the moon, the fish is a non-renewable isotope that could power empires for centuries. This creates a first-mover advantage that feels less like a scientific mission and more like the Wild West. If a private corporation or a state-backed entity sets up a mining perimeter, establishes the only communication relay in the sector, and begins processing helium-3, they effectively control that territory through de facto presence. By the time international courts in The Hague even begin to debate the legality of a claim, the infrastructure will already be hardened on the ground. We are already seeing the lines being drawn. On one side, the US-led Artemis program seeks to establish safety zones around lunar operations to prevent harmful interference. To a rival nation, those safety zones look a lot like illegal annexations. While we imagine a war for the moon involving lasers and starships, the reality will likely be much colder. A silent war of lawyers, orbital frequency jamming, and strategic claim jumping. But this land grab isn't just about planting flags, it's about energy independence. In a world currently scrambling for lithium, cobalt, and rare earth minerals, helium-3 represents the ultimate escape hatch. The nation that secures the far side doesn't just win a race, they potentially secure a 1,000-year monopoly on the world's cleanest and most powerful energy source. The stakes couldn't be higher. If the transition to fusion happens, the far side of the moon will become the new Persian Gulf. Every trench dug and every satellite launched is a move in a high-stakes game where the winner takes all. But as we look toward this glowing future, we have to ask, is this the beginning of a post-scarcity utopia? Or are we simply exporting our oldest conflicts to a new world? For 4 billion years, the far side of the moon has sat in total silence, shielded from the noise of Earth. But that silence is finally coming to an end. We are no longer viewing the moon as a distant light in the sky, but as the essential power station for the next millennium. Establishing the infrastructure for a helium-3 harvest could rewrite the fundamental human story. In the best-case scenario, we witness the end of the global energy crisis, a world where carbon emissions are a relic of history and clean electricity is abundant for every person on the planet. The far side becomes the gateway for a post-scarcity civilization built on the hard-won lessons of our collective past. But a darker path remains visible if the far side becomes a lawless frontier of safety zones and corporate monopolies. We aren't just mining for fuel, we are exporting our oldest conflicts to the stars. If this new Persian Gulf leads to the same cycles of violence and inequality as the old one, we've simply moved the battlefield 384,000 kilometers away. This is a high-stakes game where the winner takes all, leaving the rest in the shadow of progress. This isn't ultimately about orbital mechanics or complex physics. It is a test of human maturity. For the first time in history, we have the opportunity to decide how a new world is shared before the first industrial drill even touches the silver dust. As we gaze into the lunar night, we are forced to look into a mirror. The moon isn't just a lifeless rock, it is a profound second chance for our species. Whether it becomes a beacon of unity or a monument to greed is entirely up to us.